Good day, ladies and gentlemen. This is the 16th lecture of the second series of lectures related to the implementation of this RM software for filter design. In this lecture, we will discuss synthesis of selective bandpass filters having a corrected group delay characteristic. The content will be as usual with a small modification. We will go first for the naming of the project, then we will introduce the design requirements, then we will perform synthesis of the transfer function and analysis of the properties of the solution, and then we will take two paths for the physical system realization. The first one goes for active, which means active RC, active SC, and digital infinite impulse response realization. And the second path goes for passive LC realization. We are starting, as usual, by activating the main program, rm1html, and allowing the blocked content. Before the real start of the design, we will visit the chart of the recommended design sequence. First, here we enter the project name and then proceed with the bandpass here, where we are introducing the design requirements. Now, we are proceeding by synthesizing a low-pass prototype. It may be of any kind, low-pass prototype, selective, non-selective, with transmission zeros at the omega axis or without, whatever polynomial. And then we perform transformation, which means we are creating the transfer function of the selective bandpass filter. From there, we proceed to the corrector BP program, which creates the corrector. So now we have a complete transfer function of the bandpass filter with corrected group delay. At this moment, we may visit the transfer function analysis or the property CSV file to check for the properties of the solution. And then we proceed with synthesis of the system. Here are listed the active versions, the digital, switched capacitor, RC parallel, RC cascade. And since the RM software cannot synthesize directly bandpass filters, we can do the synthesis of the all-pass part of the transfer function. So this program, Cascade AP, will create a circuit which is passive LC performing the all-pass function. To complete the schematic of the bandpass filter as a passive LC, we have to go backward to the low-pass prototype design and do whatever we did at the beginning. So create the transfer function of the low-pass prototype and then directly synthesize the bandpass selective circuit. And then we will have two circuits, two SPICE files, one created by Cascade TR and the other Cascade AP, which may be merged by the Cascade by the merger program, which will create a SPICE file which needs some work as advised within the file to be completed. So let's go now to the synthesis. We will name the program, the project, band pass corrected, and we will proceed with bandpass filter design, and here are the requirements. We will ask for 100 kilohertz, 120 kilohertz, the upper limit of the passband, 160 kilohertz, the lower limit of the stop band, the upper stop band, then 80 kilohertz for the lower limit of the passband, 40 kilohertz for the lower limit of the lower transition band. The maximum passband attenuation will be 3, the minimum stop band will be 40, asymptotic slope will be only 6, the group delay error will be 5%, and the normalized resistance 1 kilo. That is the input requirements are completed. Now we will proceed with synthesis of the transfer function. It will be a critical monotonic since we got 3 dB for the passband, and we choose the least square monotonic transfer function and 7th order filter, which is a little bit lower than the proposed here, since we are introducing zeros later on. Now the monotonic polynomial filter is synthesized, and we will proceed by correction of the amplitude characteristic, which means we will introduce transmission of zeros. We will go with 6th order numerator, and now we have a new transfer function of the 7th order filter with 6th order numerator. That is enough to start the transformation. So we are transforming into a bandpass and run the transformation, which is very fast, which means now we have a transfer function of a selective bandpass filter. What we need is to correct the group delay characteristics. So we will go backward to the amplitude or phase correction, and this is the program. This is the branch will allow group delay corrected selective bandpass filter synthesis. What we need to introduce here is the order of the corrector, which will be 4 here. And now, since we are going after the passive synthesis, we will introduce number 1 here, and that will allow creation of the proper information for passive synthesis. Now the corrector BP is running, and since it's lasts a little bit longer, we will pause the recording, and we will wait for the program to finish the synthesis of the corrector. Now, since the optimization procedure is finished, we have a corrected transfer function, and we may see now how the results looks like. We will stretch a little bit the frequency axis. Here we will put, let's say, 60,000, and here 140,000. So this is the attenuation. This is the phase characteristic. This is the gain, and that is the group delay, overall group delay of the resulting filter. Now we may proceed with synthesis. And we will go first for the RC cascade. Here we will look for the SPICE file, which was just created. And of course, everything is okay. Now we will go for the HTML report, and this is the schematic, which contains the filter cells and the all-pass cells, and again a filter cell. And so all together it is 2, 4, 6, 2, 4, 8, 12, 14, 14th order of the filter and 4th order of the corrector, and of course there is a cell which is representing the transmission 0 at 0 at infinity. Now we proceed with RC parallel. Here is the, and I will go only for the SPICE file here. Here it is again, of course. Now I will go for the SC sampling frequency 10 megahertz. 1 picofarad is the normalizing capacitance. And now we may run the synthesis. Done. And here is the SPICE file. And again, we will not wait for the complete response, which since it will take time, but we will look for the schematic. Here it is, and we have now all the cells are of the same structure, but there are, of course, 9 cells zooming, and of course the complete schematic. the next is to go for the digital. Again, the same sampling frequency. And here is the transformed into a digital. Now we will look for the here it is, CSV file. To see the response of the digital filter. And again, we will stretch the x-axis from 60,000 kilohertz to 140,000. And here is the amplitude characteristic, here is the phase characteristic, here is the gain, and here is the group delay, and you can see that is slightly distorted by the bilinear transform. Now, the final step is to go for the schematic of the corrector, which will be done by the Cascade AP. Done. And what we should do now, if we want to create a passive LC realization, we must go backwards toward the low pass transfer function synthesis, which will be the same like the one which was already synthesized, but the files created in the meantime were distorted, so we have to regenerate these files. We go for the least square monotonic. The order of the filter will be 7th order. Now we have the critical monotonic, least square monotonic. Now we will go for amplitude and phase correction. We insert the transmission zeros. The order will be 6. And then we will create the low pass prototype, which now goes directly to LC synthesis by the Cascade TR program. Now we have both files, but to put them together, we will activate the merge program, which is done. And now we will look for the merge spice file, which needs to be corrected a little bit by eliminating the load resistor of the selective part and by introducing the output terminal node of the filter to the input terminal node of the corrector. Done. Now we may run them. Oh, I did something wrong. This is 17 here. It should be 7. That is. And here is the group delay. And I will adjust the scale here. As you can see, the top is about 100 and the bottom will be only 10 for our purposes. And this will be 10 the step. So we have the same group delay shape of the group delay characteristic like with all other examples. So that will finish the presentation, the lecture, which describes how selective bandpass filters with corrected group delay characteristic may be created.